Hey, PAP Chemistry, how are we doing today? Mr. Oglesby here. So today we are going to be continuing our notes on types of reactions. Now for this, I would highly suggest you have a periodic table because you will still need to know how to write those formulas for those different compounds that we are talking about today. So let's go ahead and get started with this. Now in this, we are going to be actually finishing these main types of reactions that we deal with in pre-AP chemistry. So last class, we talked about synthesis and decomposition reactions, right? We know that with a synthesis reaction, we take two or more reactants and we end with one product. And then with decomposition, it is the opposite of that. So we're going to take one reactant and we're going to end with two or more products. Now, in a single replacement reaction, which is going to be the first reaction that we deal with today, what we're going to see is we have one element and compound as the reactants, and then your products are also going to be one element and one compound, okay? And so I like to think of this as a partner swap. So think of it like you're dancing out on a dance floor, you're dancing with somebody, and then the next kind of in the middle of the dance, you're swapping partners and you're dancing with somebody else, okay? So it is going to be what we call single replacement. And again, this would be a representation of that. So I've got element Y right there. And then I've got my compound, which is a compound of B and X. And they're going to produce element X with a compound of B and Y. So looking at that reaction, basically what you see is that Y is replacing X. And that leaves X out by itself. Okay, and then Y would be partnered up with B there. So again, a little Star Wars thing for y'all to see there. So here we've got Han and Leia plus Luke, and that produced Luke and Leia plus Han. And so just kind of swapping partners in the midst of their dance. Okay, so what is happening in a single replacement reaction? Well, essentially all it is one element replaces another. So one element replaces another in a compound. ANOTHER. Okay, one element replaces another in a compound. Now, this doesn't just always happen, right? We don't always see one element replacing another. Why? Because as soon as that reaction happened, then it would immediately go back and replace itself. And you would see this constant like back and forth of those reactions where one is replacing it and then it's replacing the other and then it's replacing back again and then it's replacing the other. And it would just keep on happening to infinity, right? And so we don't actually see that. What we do see is that there are certain elements that can replace other elements. And we base that on what we call the activity series. And that's what this little thing is over here on the right side of your notes. So with your activity series here, basically what this is saying is that as I move up, the element becomes more active, and so it will replace everything below it. And so looking at this, we know that lithium is able to replace everything below it here. So lithium can replace rubidium and potassium and barium and calcium and sodium and magnesium and so on, right? And so that's kind of a big important thing to recognize in this is that with single replacement reactions, we have to check our activity series to make sure that the substance can replace another substance. Now, there are two places on the activity series that you do need to keep in mind. And that is what these two lines right here represent. Okay? So this top line right here, what this tells me is that this can replace everything above it. So everything above it can replace hydrogen in water. Now we know that the hydrogen in water, there is going to be a strong bond there. It's holding very, very tightly to that water molecule, right? And so because of that, we do require a higher activity series for that to actually replace the hydrogen in water. This line right here, again, it has to do with replacing hydrogen. So it will replace hydrogen in an acid. Okay, and remember, acids are going to be those compounds that start with hydrogen. Okay, so those two places are going to be something to kind of keep in mind because I might not be able to replace some hydrogens depending on what substance it is bonded with. So depending on what the compound actually is. Okay. The other thing that I do want to remind you of is that water can be written as HOH. And we write that as HOH because, again, it does a lot of times help me, especially specifically when I'm balancing a chemical reaction. It also helps me with the single replacement reaction because that hydrogen right there at the beginning is going to be what is replaced. And so we would have a hydrogen ion that's replaced, and we would be left with a hydroxide ion. Okay? So let's take a look at this first one right here. So I've got iron and silver sulfate. So iron is Fe plus silver sulfate, Ag2SO4. And what we want to know is, will the iron replace the silver? Now, how do I know that it's trying to replace the silver? Well, metals replace metals, nonmetals replace nonmetals. And so we're looking to see, will that cation replace that other cation? Was that metal replace the other metal? So looking at this, I'm trying to see if iron can replace silver. So again, I look over here at my activity series. I have iron right here, and I have silver right here. Well, is iron more active than silver is? Yes, it is. So since iron is more active, then we know that it can replace the silver. And so what we'll see is that iron kicks the silver out. So we would get iron sulfate and silver. Okay. Now, one question you might ask is, how did I know that this is the formula for iron sulfate? Well, I just used the most common charge for iron, which is a +2 charge. A lot of times we'll actually give you what the charge actually should be. Okay, so do keep that in mind. So iron, 2, and sulfate, we know that iron has a +2, sulfate has a -2. They cancel out, and we would get that as our compound. Now, the last thing we would need to do is go back in and balance. To balance, I would just need to come over here and put a 2 in front of that silver. Okay? Now, let's go ahead and move on. So I actually want y'all, based off of what we just did, to give this next one an attempt. So I want you to pause your video, work through this next one, and then we'll go over it. Okay? So pause your video. All right, now this is what you should have ended up with for this reaction. So first off, I would need to check my activity series to see if my aluminum was able to replace my hydrogen. Now, that is in an acid, so I would double check and make sure that aluminum is above this first line here. And so looking at this, I see that aluminum is right here, so it can replace it in the acid. Now, here's a question. Could this aluminum replace hydrogen in water? Well, no, it's not, because it is not high enough on the activity series to replace that hydrogen in water, which is signified by that line right there. Okay, so do keep that in mind. So if you had aluminum plus H2O, then what we would see is actually no reaction. Okay. All right. Next one, potassium and water. I'm going to do this one with you because, again, we've got water, and I want to remind y'all that water gets separated into HOH. So here I've got potassium and water. Now, water is H2O, but again, remember to write that as HOH. Now, why do I want to do that? Well, I want to do that because if I don't, then I'm going to assume that potassium is trying to replace both of those hydrogens, but it's not. Potassium is just trying to replace this first hydrogen, which is right here. Okay? So I'm going to go ahead and erase that. I'm going to put HOH up here just as a general reminder of what you should be doing. We know that this potassium is trying to replace that hydrogen. Okay? Well, now I need to look at my activity series, and I'll see, okay, well, potassium is right here. So since potassium is there, is it high enough on the activity series to replace hydrogen in water? Well, yes, it is. So since it is high enough to replace hydrogen in water, we will get potassium hydroxide and hydrogen gas. I would need to go back in and balance, which would require I do a 2 here, a 2 here, and a 2 right there. And so that would then be my final formula. Okay. Now, we're going to skip the next one. I'm going to leave it for practice for y'all. And I'm going to go ahead and move on to this very last one. So it says silver is dropped into hydrochloric acid. So silver is Ag, and it's dropped into hydrochloric acid. So I'm trying to see if silver can replace hydrogen. Again, I need to go back in and check my activity series. Silver is right here. Can it replace hydrogen in hydrochloric acid? Well, no, it cannot. It's not high enough on the activity series to replace that hydrogen. So I would just write no reaction. Now, does it need to be all caps? No, it does not need to be all caps, but I do think that really kind of emphasizes no, there's no reaction that happens here. So silver would just sit in that hydrochloric acid and nothing would occur. Okay? All right, so now we've got our next reaction. But before that, I do want to show y'all another quick video on a demo of just that single replacement reaction actually occurring. Okay? All right, y'all, so this next reaction is a single replacement reaction. So for this, I've got some copper wire, and we just kind of twirled it up there, and drop it in there. And then I've also got some silver nitrate solution. And so all I'm going to do is just pour this into there, and we're going to see what happens. All right, so now let's look at double replacement reactions. So double replacement reactions are going to be very similar to single replacement in that one element's replacing another element. But in this case, we've now got two compounds doing this at the same time. And so what we're going to see is that element A is going to swap places with element B, essentially. So element A would then be paired up with Y, and element B would be paired up with X. A lot of times what I'll hear is that I pair in with in and out with out. And you're like, okay, well, what does that mean? Well, so in with in would be, okay, well, that's on the inside and that's on the inside. Okay, so if we're looking at that entire reactance, those two elements are on the inside of everything else. And then this would be out with out. So I would pair B with X and A with Y. Okay, so in with in and out with out. Double replacement, you're just swapping those partners. Okay. Now, we do just assume that this reaction is going to occur. And so for that reaction to occur, those elements do need to swap places. So that would be our description. So elements swap partners, which is, again, just the places that they're in. Okay, and that's going to form new compounds. Remember that anything that produces a solid is what we would consider a precipitation reaction. So if we're looking at these double replacement reactions, some of them are actually going to produce that precipitate that we've talked about in the past. Now remember, a precipitate is going to be that insoluble solid that forms by mixing two aqueous solutions. Now when we talk about net ionics and solubility rules, which is here in the next couple of weeks, then we'll kind of go over how you figure out if something is a precipitate or not. Okay, but really, if you do the reaction and it produces like a little fine powder, or if a solid like gel-like substance appears, then you do see that a precipitation reaction did occur. Okay. All right, so how do I actually do a double replacement reaction? Well, double replacement reactions, again, they're just swapping their partners. So here I've got potassium iodide, so that's Ki, and lead nitrate, so PbNO3, 2. And this is a double replacement reaction. How do I know? Because I've got a compound and a compound. So in double replacement reactions, we've got two compounds producing two new compounds. Every single time, you've got two compound reactants and two compound products. So all that's happening is we do in with in and out with out. So outside with outside would be K paired up with NO3, and inside with inside would be lead paired up with iodine. Now, a big common mistake that students make here is they just write K, NO3, and then I, PB. So they don't swap places. Remember that in these substances, you should always write your cation first, okay? So I have KNO3 plus PBI2. And then that would be my formula there. That would be the entire chemical equation. We would need to go back in and balance. And so to do that, all I'm going to do is I'm going to put a 2 right here and a 2 right there. And then that would be my balanced chemical equation. Okay, so this is very, very simple. Double replacement, I find, is one of the easiest things because there's not really any rules that you have to know. You just have to look and see, okay, well, these are just going to swap partners with who is paired up with who. Okay, so I want y'all to pause your video and actually solve this next problem on your own. Solve this problem, we'll talk about it, and then we will move on. All right? All right, so this is what you should have ended up with. So I should have ended up with sodium iodide, NaI, plus HC2H3O2 produces NaC2H3O2 plus HI. So again, all that's happening is we're swapping what's paired up with what. What cation is paired up with what anion. All right, I'm going to leave that next one as practice for y'all. Again, you should be able to check the key and double check your answer from there. Okay. Now, the very last thing that I want to point out with decomposition, there are 3 times that you will see in a decomposition reaction, we have more than 2 products. And really what's happening is that we've got this intermediate step. So we've got this time when they start to decompose, right? So, or they not start to decompose, where they swap partners, but as a part of swapping partners, now one of the things that's produced is actually going to break down even further. And so here I've got water and barium carbonate. So anytime I have carbonic acid there, it's always going to decompose into carbon dioxide and water. Now remember, that's one of your decomposition rules. So if we have one of these as if I've got H2SO3, that's going to form and decompose into sulfur dioxide and water. And then if I've got ammonium hydroxide, that decomposes into ammonium gas or ammonia gas and water. So those 3 things you do need to keep in mind. Those are what we would call the exceptions. You do need to have those ready to go when you are taking your test because those are always a possibility. Okay. So here I've got water and barium carbonate. So I've got HOH and barium carbonate, BaCO3. And then that is going to, first off, go through double replacement. So in double replacement, we do in with in and out with out. So I'm going to do BaOH2 and H2CO3. Now, looking at this, I did produce one of my exceptions. So what I would need to remember is that this is actually going to turn into carbon dioxide and water. And so that would then turn into what our formula is actually going to be. Okay, you would need to go back in and balance your equation here, which would end up being a 2 right there at the front. Okay, so again, that would be the exceptions that we can see. So do keep those in mind. Make sure you are prepared for when those are going to happen. All right. All right, so now that we've finished double replacement reactions, and we've talked about them a little bit, let me show you a quick demo on those double replacement reactions. All right, y'all, so the next reaction we have is a double replacement reaction. I'm going to have some lead nitrate and some potassium iodide, and I'm going to mix them together. So I'm going to start with the lead nitrate. Put quite a bit in there just to make it a little easier to see. And then I'm just going to add a couple of drops of the potassium iodide. And so what you should see there is that little powder, chalky-like substance that appears there on top. Now what I can actually do with that is I can actually heat that up for about an hour. So a really long time of heating it up. And then afterwards, let it cool overnight. And what can happen is it turns into this right here. So we call this gold rain. And so if I shake it up, which I'm going to move this out of the way for you, it actually looks like little bitty gold flakes floating around on the inside there. That would be your lead, nitrate, and potassium iodide. Okay, so now let's talk about combustion. So combustion tends to be what you think of as combustion. It's going to be that reaction that we see fire produced, where we see some kind of ignition, something that, a lot of times we say explodes, right? And so this is a very fun reaction to see. It can be a very dangerous reaction that occurs, right? But for combustion to occur, we need two things. The first thing that we need is called a hydrocarbon. And a hydrocarbon is typically going to involve a carbon and a hydrogen. And then sometimes you will see that nitrogen, an oxygen, or a phosphorus that is going to be attached to that. So you could see like glucose technically is a hydrocarbon, right? You've got C6H12O6. And so you've got that carbon, that hydrogen, and then there's also an oxygen attached to that. Methane, ethane, propane, those are all hydrocarbons. And so those can all go through combustion. So that's the first thing that you need. The second thing that you need is oxygen. If you do not have oxygen, you cannot have combustion occur. And so when we're looking at a combustion reaction, just because something produces fire does not necessarily mean it's going to be combustion. To be combustion, you need 1, the hydrocarbon, and 2, the oxygen. If you don't have both of those, it is not combustion. It's a different type of reaction. Okay? So the nice thing about combustion is that it can, or it always produces the same two products. It is always going to produce CO2 and H2O. Every single time you're going to get CO2 and H2O as a part of that combustion reaction. Now, if you do have nitrogen or phosphorus, you could produce something else as well. But typically when we see a combustion reaction, it is going to be producing CO2 and H2O. A lot of times students ask, okay, well, as a part of combustion, we're producing carbon dioxide and water. Well, what do you typically use to put out a fire? Well, you typically use water, right? So one of the things that this combustion will produce is what would normally put it out. Now, why didn't it put it out? Well, it doesn't put it out because you've got enough energy being released that it's turning that water into steam, which is a part of that smoke. Okay? All right. So I know that a combustion reaction always has a hydrocarbon and an oxygen, and it will always produce carbon dioxide and water. Okay, so those are the things that I know about combustion, and it's the same every single time. Okay, so looking at this reaction, I know that this is going to be combustion. How do I know? right here, I have a hydrocarbon. Okay, hydro, think hydrogen, carbon, think carbon. So you've got to have hydrogen and carbon present in that reaction. Okay, and it's a part of a single compound that we have that hydrocarbon. We also need to have oxygen as a part of this reaction. So if I just had the hydrocarbon but no oxygen, it is no longer combustion. Okay, so this is going to produce always, every single time, CO2 and H2O. So combustion is very easy. I don't have to think about what's being produced because it will always be CO2 and H2O. Okay. The very last thing we would do would be to go in and balance. And so I'm actually just going to go ahead and balance that for you very, very quickly, just because I think that y'all probably have balancing down at this point. If you don't feel like you do, then I would suggest that you practice on your balancing because it is a very important thing in this topic. Okay, so we would have 2 oxygen and 2 H2O, and then that would balance out our chemical equation here. Okay. All right, this next one is a little bit more tricky in that you see we don't just have carbon and hydrogen in that hydrocarbon, but we've also got oxygen. So how do I do it? Well, I do the exact same thing. I know this is combustion because this is a hydrocarbon and it's reacting with oxygen. So it is always going to produce CO2 and H2O. So I don't even have to think about that. I immediately know it's going to make CO2 and H2O. Then I would go back in and balance. What makes this one a little trickier is the balancing is going to be a little bit more difficult because of that oxygen that's in that first compound there. So how do I do it? Well, my suggestion is you always balance your oxygen last, and that will make this easier. Okay, so always balance your oxygen last. But when you do that, you're going to get a 2, a 3, a 2, and a 4, and then those would be my coefficients for that. Okay. So I want y'all to take a second and solve this very last combustion problem. So pause your video, solve the problem, then we'll go over it. All right? Okay, so this is what you should have ended up with as your answer. So we should have had C3H4 plus 4O2. Now again, I knew this was combustion because it's got a hydrocarbon and oxygen, and that produced 3 carbon dioxide and 2 water. All right, y'all, so there is one more quick demo for y'all to see over combustion. But once you finish that, hopefully y'all have a great rest of the day. Let me know if y'all have any questions, or let Mrs. Treese know if y'all have got any questions. But otherwise, we will talk to y'all later. Bye, y'all.
All right, guys, so this is called the Whoosh bottle. All right, I'm going to take my bottle, and I'm going to put some ethanol in it. Ethanol is a type of alcohol. All right. Now I'm going to spread it around all the sides of my jar.
Why do you need to do that?
Oh, I need to do this. I'm trying to get it nice and coated, as well as I'm trying to turn some of it into a vapor. All right, let's give it a second to drain. Here we go, guys. Our next demo is going to be combustion. What I have is I have some bubbles that I've blown that are filled with methane. That's the gas that comes out of our pipes here. All right, let's see what happens. Pretty cool. Now, let's try to do some, I'm going to zoom out a little bit. I'm going to try to blow some up and get some catching on fire mid-air.